Okay, we're going to look at the shape of a geometric distribution. I want to prove results for total probability and expectation. I won't do variance because it's quite long, but if you're interested, I'm really happy to go through it with you in class. So if we start with the shape, so if x is geometrically distributed, p is 0.3, then this is basically the probability that x equals r, and these are your values of r. Obviously this keeps going on, so it's an infinite distribution. So the probability x equals 1 is 0.3. The probability x equals 2 is 0.7 times 0.3, so you get 0.21. And then timesing by 0.7 each time, your shape will come down roughly like this. So you can see you're coming down and probability x equals r equals 0. This horizontal axis is going to be an asymptote to the curve if you were going to join this up with a smooth curve. One thing to notice, and this is true of any geometric distribution, is the probability x equals 1 will always have the highest probability. So there's a single probability that will always be the case, and then obviously the shape of the curve will vary slightly depending on p. So that's the shape. General results. So if you imagine, so if you think about the work we did on discrete random variables, if you have r and the probability x equals r for a geometric distribution, r is taking values starting at 1, not 0. And it continues, so it's an infinite distribution. The probability x equals 1 will just be p. The probability you get your first success on the second trial, qp, q squared p, qqp, q to the 4p, and so on. So you can see your probability distribution quite clearly there. And we need the total probability, so we need the sum of all of these to equal 1. So total probability and we can prove that this is the case, so that the sum from r equals 1 to infinity of the probability x equals r is equal to p plus qp plus q squared p plus qqp plus etc. I've got a p running through all of those, which I can take out as a factor. And then we end up with a geometric series in here. Apologies if you're in my maths group, because we haven't done geometric series yet, and I don't know whether you've done them if you're in Jamie's group. But if you have a geometric series, the sum to infinity is a over 1 minus r. A is your first term, and r is the common ratio. Sorry, my writing's gone a bit scruffy. So r is what you multiply by to get to the next term. And we'll be doing that in maths in about a week's time. So you can always come back to this then. So my first term is 1, and I'm multiplying by q each time to get to the next term. So it's 1 over 1 minus q. 1 minus q is equal to p. And so you can see there that the sum to infinity of these probabilities added together is equal to 1, which it needs to be, or it wouldn't make sense. I was going to say something else. Yeah, when we do negative binomial, I do a proof on that as well, but you can see this is a geometric distribution and it's using this sum of a geometric series. So you've sort of got a geometric series embedded in there. And when I show you the proof for the negative binomial, you end up with a negative binomial distribution embedded within these proofs. So it kind of gives a bit of meaning to that name, geometric. So you've actually got a geometric series embedded within that sum. I'll do the same for expectation, but I won't prove the variance. I think it's good for you to see some of these big proofs. You don't need to know them for your exam. So for the expectation, so the expectation of x is equal to 1 times the probability x equals 1 plus 2 times the probability x equals 2 plus 3 times the probability x equals 3, etc. And again, that's going on to infinity. The probability x equals 1 is p. The probability x equals 2 is qp, but I'll write that as pq. The probability x equals 3 is, you won't have got a success twice, so it's pq squared, and then it'll be 4pq cubed, etc. So I can now pull a p out again, and we end up with 1 plus 2q plus 3q squared plus 4q cubed plus, in that bracket, sorry, that should be a squared, I don't know why I wrote cubed. There. And if I let s equal the expression in the bracket, and then this little proof is a bit like proving the sum of a geometric series. I'm going to times q by s, or s by q. So I'm literally just timesing through by q. To there. And then I can do the first minus the second. So I can do s minus qs. And that will give me 1. 2q minus q is q. 3q squared minus 2q squared is q squared. 4q cubed minus 3q cubed is q cubed, and so on. So this takes us back to our infinite series. I'm going to pull s out as a factor here. This is equal to a over 1 minus r, as before. And then if I divide by 1 minus q, s is equal to 1 over 1 minus q squared. 1 minus q is p, so that whole expression is equal to 1 over p squared. S is this expression here, and so the expectation of x is equal to p times 1 over p squared, which gives you 1 over p. So couple of results you need. These are in the formula books, you don't have to remember them. So one's for expectation of a geometric distribution and one's for the variance of a geometric distribution. I'll write them again out on here, I think. I won't do proof for variance. I have it, so I have it here. Ta-da! If you want me to go over it with you, I'm actually very happy to. I quite like doing proofs. So the expectation of x is 1 over p. I've just proved that. And the variance of x is 1 minus p over p squared. So you need those two results. So that's if x is geometrically distributed with parameter p, and they're both given in your formula book. So what I'll do probably in my next video, actually, because I'll run out of memory otherwise, is just go over a couple of examples using these. And then that's kind of it for geometric plan. We have to do a little bit of hypothesis testing, but we won't do that yet.